in most things you've dealt with in mathematics so far, you've dealt with the idea of an explicit equation. So what an explicit equation is when I can get one variable by itself and write it as a function of the other variable. So y equals some jumble of terms involving x. But an implicit equation is something where these terms are coupled together. So over here I have something called xy equals 1. And that's implicitly defined, and we can actually separate that out and determine that that can be written explicitly. However, it's very, very often the case that we don't have that luxury. So given this, y sine of xy equals x minus y squared. Now you could try to multiply that out and do a lot of algebra and really frustrate yourself, but you're not going to be able to turn this into something where it's y equals something where it's only x's. If you can, let me know. We have to talk. But nonetheless, that doesn't mean this isn't a useful term to us. It isn't somehow a useful equation to us. In fact, a lot of real-world applications involve this type of modeling. They have these very coupled equations that don't have nice, simple ways to have solutions. So what we can do is we can solve for points at which the equation's valid. So like looking at this, if I plugged in the point 0, 0, well, at this point sine of 0 is 0, so it doesn't matter what y is. And then 0 minus 0 is also 0. So I have 0 on the left and I have 0 on the right. So that tells me that 0, 0 is a solution to this equation. It's a point. If I were to graph this relationship, it's a point on that graph. And also, square root of pi times square root of pi, or square root of pi for x and square root of pi for y is a solution to this equation, because sine of pi would be 0. Square root of pi minus square root of pi would also be 0. And there's many more, but those are two off the top of my head that I could think of. Now, what I can do is then I can say, all right, well, now I have, maybe I can use a computer. Maybe I can do all kinds of stuff to figure out a bunch of points on the graph, and maybe I could construct it. But I might want to figure out, if this is my model, I might want to figure out how it's moving. How are the points kind of flowing together? Because what I end up with is, since I'm not going to have a function where y is a function of x, we don't have that natural progression, right? If you see y as a function of x, like a parabola, you know that the parabola is moving this way. But if I had something like a circle, how do I know if it's moving counterclockwise or if it's moving clockwise? Or maybe it's like randomly jumping all around and drawing. I don't have that luxury. So what I can do is I can develop this idea of I can use this idea of a derivative to develop an understanding of this flow. How at this point, where's it moving? Where's it going next? And that can give me a much richer understanding of what's happening. And so we use this process called implicit differentiation. And so implicit differentiation that we're going to learn about is it's going to synthesize all the things we've learned so far about the product rule and the quotient rule and the chain rule. And it's going to help us put those together to try to solve an equation for what y prime is, and then we can find y prime at specific points. So, for instance, using that methodology, what we actually find is at 0, 0, the derivative is also 0. So, if there is kind of no flow, it's kind of at a sticking point. Now, that may mean that it's not moving quickly. It's probably at like a maximum or a local minimum. And we'll talk about that more as we move along. But here what we see is the derivative is negative, so at pi, or square root of pi, square root of pi. So that tells us that this thing is decreasing over that time, so we can expect it to be going downward.